Hello everyone. Today we shall discuss about the chapter that is power. Power we have completed. So today we will discuss about collision. Now see how we can um, discuss these things about collision, and let us see how we can discuss this thing that is about collision. Now see how it can be done, that is important for us, and you see how it can be. So friends, first of all, we learn the definitions of collision. After that, we'll go to the various uh, examples of collision and let us see how it acts. Okay, here you see we are defining this one by one. So, what is collision, that I'm going to discuss with you. So, the first thing you have to remember that in collision, what are the various factors that I am going to deal with. You see here, the first one is, now you see, the first we have, we will take a page, and after that we will start the chapter collision, and let us see how we are going to start this one, that is this chapter. Let us see and what we are getting. You see here. You'll find it here that we are discussing the chapter collision. Let us see how. Now let us find about collision and see how we are going to discuss these things, right? First of all, you see here that we are discussing about collision. Collisions. Now, first of all, we deal with the collision, and you see there are various cases of collision that we are going to deal with. Collisions. And you see here in physics, we study motion. There is change in position. In physics, we study motion. In physics, in physics, we study motion. In physics, we study motion. Physics, we study motion. We study motion. Motion means change in position. Change in position. Change in position. At the same time, we try to consider physical quantities. At the same time, at the same time, the same time, we try to discover, we try to discover, try to discover, we try to discover physical quantities, physical quantities, physical quantities, physical quantities which do not change in physical process, which do not change, which do not change, we do not change in physical process, in physical process, in physical process. The laws of momentum and energy conservation are typical examples. The laws of momentum, the laws of momentum, the laws of momentum, momentum and the laws of momentum and energy conservation and energy conservation, energy conservation conservation are typical examples are typical typical examples. In this section we shall apply. In this section, in this section, we shall apply. In this section, we shall apply. In this section, we shall apply. In this section, we shall apply these laws. We shall apply these laws. These laws to a commonly encountered phenomena. To a commonly to a commonly to a commonly encountered phenomena encountered co encountered phenomenon encountered phenomenon, namely collisions, namely collisions. Namely, so we are considered with collisions. Let us find that in collisions what we get. So we are considering about collisions. Several games several games, several games such as such as billiards, billiards, marbles, or carom involve collisions, involve collisions. We shall study the collisions of two masses in idealized form. We shall study we shall study we shall study the collisions of two masses. Study the collisions of two masses. The collisions of two masses. Collisions of two masses. Collisions of two masses in an idealized form. In an idealized form. In an idealized form. So, consider two masses. Let us consider two masses. Consider two masses M1 and M2. M1 and M2. The particle M1 is moving. The particle M1 is moving. Particle M1 is moving with speed. V1I. The subscript I, implying initial, initial. We can consider M2. We can consider M2 to be at rest. To be at rest. No loss of generality is involved in making such a selection. No loss, no loss of generality, no loss of generality is involved in making such a selection. In making such a selection, making such a selection, such a selection. In this situation, the mass M1 collides with the stationary mass M2, and this is given in figure. In this situation, in this situation, in this situation, in this situation, the mass M1, the mass M1, the mass M1 collides with the stationary mass M2, collides with the stationary mass M2, with the stationary mass stationary mass M2, stationary mass M2, and this is given in figure, and this is given in figure below. It is suppose this is mass M1, this is mass M2, M1, and the velocity is v1 initial. This mass is M2, this mass is M2. You can see here, if this direction is x, if this direction is x, then we find here that this is y direction. This is y direction. And if we find here that in this direction M1 is going, M1 with velocity v1 f, velocity of mass M1, final velocity, and this direction M2 is going. That is M2 at this direction, M2 is going, this direction M1. This is M2, and the velocity will be v2 f, means final. And this is, suppose this is angle theta 1 with x direction, and this is theta 2 with x direction. And what we'll find, you can find from here. The masses M1 and M2 fly off in different directions. The masses M1 and M2, the masses M1 and M2 fly off in different directions. In different directions. we shall see that we shall see that we shall see that there are relationship that there are relationship relationship which connect the masses is a which connect the masses which connect the masses which connect the masses, the velocities and angles, the velocities the velocities and the angles and the angles. Now we have two types of collisions. Now we'll deal with types of collisions. After that, we will find a collision in one dimension and a collision in two dimension. Now we learn first about elastic and inelastic collision. What is the difference and how we find this one. Now we learn with elastic and inelastic collision. Elastic and inelastic collision and inelastic. What is the difference between them and how can you deal with these two things, elastic and inelastic collision, that we are going to deal with. In all collisions, the total linear momentum is conserved. In all collisions, in all collisions, in all collisions, the total linear momentum, the total linear momentum, the total linear momentum, the total linear momentum is conserved. The total linear momentum is conserved. The initial momentum of the system, the initial momentum of the system, the initial momentum of the system is equal to the final momentum of the system is equal to the final momentum of the system, to the final momentum, to the final momentum the final momentum of the system, final momentum of the system. One can argue this as follows. One can argue this as follows. When two objects collide, when two objects collide, when two objects collide, the mutual impulsive forces, the mutual impulsive forces the mutual impulsive forces acting over the collision over the collision time acting over over the collision time acting over the collision time. So here we find that over the that is when two objects collide, the mutual impulsive forces acting over the collision time 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 del t can cause cause a change cause a change in in their respective momenta in their respective momenta in their respective momenta. So here you get del p1, that is change in momentum. You get the value as f1 and 2 del t, and del p2, that you are getting force 2 and 1 into del t. We consider it del t, right? So where F12 is the force exerted on the first particle, where F12 is the force exerted is the force is the force is the force exerted on the first particle exerted on the first particle on the first particle on the first particle by the second particle by the second particle the second particle if 21 is likewise the force exerted the force exerted on the second particle on the second particle on the second particle second particle by the first particle by the first particle by the first particle. Now from Newton's third law, from Newton's third law, Newton's third law, Newton's third law, if force 1 and 2 is equal to minus F 2 and 1. This implies This implies del P1 plus del P2 equal to 0. The above conclusion is true even though the forces vary in a complex fashion during the collision time del T. The above conclusion, the above conclusion, the above conclusion is true even though the above conclusion is even true. The above conclusion is true even though the forces vary in a complex fashion in a complex fashion during the collision time during the collision time del 2. Since the third law is true, since the third law is true, at every instant, since the third is true at every instant, the total impulse on the first object is equal and opposite to that on the second to that on the second on the other hand, the total kinetic energy of the system is not necessarily conserved. On the other hand, the total kinetic energy of the system, the total kinetic energy of the system, kinetic energy of the system is not necessarily conserved, conserved, not necessarily conserved. The impact and deformation during collision may generate heat and sound. The impact and deformation, the impact and deformation during collision may generate heat and sound, may generate heat and sound, generate heat and sound, heat and sound, heat and sound. Part of the initial kinetic energy is transformed into other forms of energy. Part of the part of the part of the initial kinetic energy. Part of the initial kinetic energy. Initial kinetic energy. Part of the initial kinetic energy is transformed is transformed is transformed into other forms of energy, into other forms of energy, forms of energy, other forms of energy, other forms of other forms of energy. A useful way, a useful way, a useful way to visualize the deformation, to visualize, to visualize the deformation, visualize the deformation, to visualize the deformation, to visualize the deformation, visualize the deformation, to visualize the deformation during collision, during collision, during collision, during collision is in terms of a compressed spring, is in terms of a compressed spring, of a compressed spring. If the spring connecting two masses, if the spring if the spring connecting if the spring connecting if the spring connecting the two masses, connecting the two masses, connecting the two masses regains its original shape, regains its original shape, original shape, original shape without loss in energy, without loss in energy, energy. Yes, without loss in energy, then the initial kinetic energy, the initial kinetic energy, then the initial kinetic energy, initial kinetic energy is equal is equal to the final kinetic energy the final to the final kinetic energy to the final kinetic energy to the final kinetic energy. Then the initial kinetic energy is equal to the final kinetic energy during the collision time the collision time during the collision time is not constant is not constant is not constant. Such a collision is called an elastic collision. Such a collision such a collision is called called an elastic collision. Such a collision is called an elastic collision. Such a collision is called an inelastic collision. On the other hand, the deformation may not be. On the other hand, other hand, on the other hand, the kinetic energy. On the other hand, the deformation. On the other hand, the deformation may not be relieved and the two bodies could move together together move together after the collision after the collision after the collision after the collision. A collision in which a collision in which the two particles move together after the collision is called a completely inelastic collision. Is called completely inelastic collision. Elastic collision. The intermediate case where the deformation is partly relieved and some of the initial condition is lost is more common and is appropriately called an inelastic collision. The intermediate case the intermediate case, intermediate the intermediate case where the deformation where the deformation is partly relieved, is partly relieved, and some of the initial kinetic energy and some of the initial kinetic energy initial kinetic energy is lost, is more common, is lost, is more common, is more common, and is appropriately called, and is appropriately 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 called an elastic collision, called an inelastic collision, inelastic collision. So this is the difference between elastic and inelastic collision, right? That is, momentum is conserved in case of elastic and inelastic collision both, but in elastic collision, that their kinetic energy is not conserved, that is elastic collision. And if the two particles move together after the collision is called a completely inelastic collision, and between the two it is known as inelastic collisions. Now we will do two things. One is we will discuss with collision in one dimension and collision in two dimension. First we are discussing with collision in one dimension. There are two types of dimension we will discuss. One is collision in one dimension and collision in two dimension. Let us find what are the various factors coming in collision in one dimension. Let us find collision in one dimension. First of all, we deal with collision in one dimension, that is collision in one dimension. See here, the first one we deal with is collisions in one dimension. Collisions in one dimension. Suppose there are two bodies, M1, another body is M2, right? And it has a velocity, and M2 suppose has no velocity, but after colliding the mass will be like this, that is M1 plus M2, and the velocity of this particle is final velocity, and this is the velocity of V1 initial, and the M2 is at rest. This is at rest, right? Therefore, this is the collision in one. Let us consider a completely inelastic collision. That is, after the collision, the mass M1 and M2 will join with each other, and we get the value M1 and M2. This is the final velocity of the total mass, right? It is after the collision we will find this one, right? Now you see that consider consider first a completely inelastic collision, a completely inelastic collision, inelastic collision, inelastic collision in one dimension, in one dimension. If it is one dimension, then if you find this angle, suppose this one is m1, and if it is it after colliding it is m1 plus m2, so here you can say that after colliding they are mixing with m1 m2. This is the final velocity, right? And the velocity of m2, let us find the velocity of m2 to be 0. This velocity v2 initial is 0. m2 is that 0 velocity. So if we take in completely inelastic collision in one dimension, then you can say that m1 is here momentum of this one, that is momentum of first particle m1 into v1f v1 initial plus this is 0, that is m2 into 0, because m2 at rest is equal to total mass, that is m1 plus m2, m1 plus m2 into vf, momentum conserved, vf final velocity, that is momentum is conserved in this case, momentum conserved, momentum conserved, momentum is conserved in this case, right? Therefore velocity final, what we are getting is this one, m1 divided by m1 plus m2, m1 plus m2. You see this one, because the momentum is 0 here, and this is a completely inelastic collision, right? Inelastic momentum is always conserved. The v velocity finally m1 divided by m1 plus m2 into v1 initial. This is equation 1, right? Then find the loss in kinetic energy and collision. The loss, we'll find the loss kinetic. In inelastic collision there is a loss. Momentum is conserved, but loss of kinetic energy is called inelastic collision. So the loss in kinetic energy, the loss in kinetic energy, the loss in kinetic energy, the loss in kinetic energy on collision is del K, the loss in kinetic energy is equal to half m1 v1 I square minus half total mass is m1 plus m2, m1 plus m2 into v final square. This is the change in loss in kinetic energy. Therefore, if we equate this one, then you will calculate the value of 1 by 2 m1 v1 I square minus we put the value of here p square here, therefore we are getting minus 1 by 2 into, if you multiply this value, in the previous case if you put the value of Vf is this one, right? So you will multiply this one, in place of this one we write m1 plus m2, and Vf is this one, you see this one from this one, that is m1 divided by m1 plus m2 plus m2 whole square into V 1i square, right? So if we get this value, then we are getting a value of 1 by 2 m1 v1i square minus this m1 m2 will cancel with 1, and this one will be m1 square. You see here, this is m1 square, and this will be m1 plus m2. This will be m1 plus m2 into v1 initial square. This is equation 2. Suppose this is equation number 2, right? From this one we got the loss in kinetic energy as equation 2. Now if we take the common, this one as common, that is this one we are taking common, 1 by 2 m1 v1i square, we are taking common, therefore 1 minus m1 is taking common, m1 divided by, this is actually half also, there is a value of half also here, you see half, so this is constant, half m1 v1 square, half m1 v1 square. So getting 1 by m1 divided by m1 plus m2 divided by m1 plus m2, we are getting this value, right? So if we calculate this one, then we are getting the value of, see, if we do m1 plus m2 minus m1, that is m1 will cancel, m2 by this one, right? So we are getting a value of half 1 by 2 m1 m2 divided by m1 plus m2 plus m2 into v1 square v1i square. This is the loss in kinetic energy, which is a positive quantity as expected, which is a positive quantity, which is a positive quantity, which is a positive quantity, which is a positive quantity as expected, right? So you're getting the loss in kinetic energy 1 by 2 m1 m2 divided by m1 plus m2 into v1 square. This is the loss in kinetic energy. So we got these two values, that is for inelastic collision. You see, collision in one dimension, it is inelastic collision. You have considered inelastic collision. Inelastic collision. This is case 1. Case 1 is inelastic collision. Now we'll define another collision, that is inelastic collision, right? This is elastic collision. This is the change in momentum, this one, and this is the loss in kinetic energy 1 by 2 m1 m2 divided by m1 plus m2 v1i square. This is the loss in kinetic energy. Now we'll consider collision, elastic collision, right? So elastic collision, this is inelastic collision in one dimension, and now we'll consider about elastic collision in one dimension. We'll consider elastic collision in one dimension, right? Let us find out this one, elastic collision in one dimension. Elastic collision in one dimension. one dimension. Elastic collision in one dimension, that we are going to discuss. Elastic collision in one dimension. Let us consider an elastic consider. Let us consider consider an elastic collision. Elastic collision. And we are taking it as one dimension, right? The momentum and kinetic energy conservation equations are, we know that in elastic collision, both momentum and kinetic energy is conserved. Both momentum and kinetic energy is conserved. Both momentum and kinetic energy is conserved. So let us find this. Again, I am talking this place as m1. The velocity is v1 initial, right? This is m2, v2 initial, right? So this is at rest first, that is v2 initial is at rest first, right? After that it goes, right? So what we are getting it here, you see here, the first, that is, we are taking the momentum. So momentum conservation, we are getting this value, it is m1 v1 initial is equal to m1 v1 final plus, this is 0, this is m2 v2 final. So after collision this will be different, right? It is in one dimension, right? So this is equation 1, suppose equation 1. And if kinetic energy is conserved, that this is momentum conservation. This is momentum conservation. And if you take kinetic energy, that is half m1 v1 I square is equal to half m1 v1 final square plus half m2 v2 final square. This is number equation 2. Kinetic energy conserved. Kinetic energy is conserved. Now from equation 1 and 2, now from equation 1 and 2, we get 1 and 2, we get M1 from equation 1 and 2. You see, this half will cancel. Therefore, we are getting, that is M1. This one half will M1 V1 square V1 I square is equal to M1 V1 final square plus M2 V2 final square, right? So this is equation 3. So from equation 1 and 3, 1 and 3 will get, from 1 and 3, this equation and this equation. 1 and 3 will get M1 V1I into V2F minus V1I is equal to M1 V1F into V2F minus V1F. This we are getting from equation 1 and 3. That is M1 V1F right. So you're getting this equation, right? Now from this equation we find that, or it can be written as, or V2F M1 will cut or we're getting V2F V2F into V1I minus V1F is equal to V1 is V1 initial square minus V1 final square, right? So we are getting this value, or it can be written also as V1 V1F V1 1 initial V1 I initial V1 I minus V1F into V1 I plus V1F. This is from the relation that A square minus B square is equal to F minus B into A plus B. This equation we have written here, right? So what are you getting here? So we are getting that number 2. Hence we are getting, hence hence V2F final is equal to V1F plus I initial V1 initial V1 initial V1 initial V2F final is equal to V1F plus V1I 1I means initial 1I I plus V1F. This is equation 4, right? Now substituting this equation in first equation. Substituting equation 4 in equation 1, we substitute this equation in, then we are getting V1F is equal to M1 minus M2 divided by M1 plus M2 into VI V1 initial and V2F and V velocity of final particle to a final is equal to 2M1 V1A V1I divided by M1 plus M2 divided by M1 plus M2. Thus the unknowns V1F and V2F are obtained. Thus the unknowns V1F and V2F are obtained in terms of knowns, that is M1, M2 and V1 initial. Special cases of analysis of what? Now we have found special cases. Special cases of our analysis are interesting. Of our analysis is interesting. Case 1. If the two masses are equal, if the two masses are equal, that is V1 F equal to 0 and V2 F is equal to V1I v1 I, right? The first mass comes to rest. The first mass comes to rest, and pushes of the second mass and pushes of the second mass with its initial speed with its initial speed. This is the case 1. If you find case 2, there will be found out right. So we are taking the case number 2. In case 2, if one mass dominates, that if one mass dominates, that is m1 is much greater than m2, that is m2 is much greater than m1, then what will happen? Then v1f is equivalent to minus v 1f. Nearly, this is not equal, but it can be said as nearly equivalent. And v2f equivalent is 0. The heavier mass is undisturbed. The heavier mass is undisturbed. The heavier mass is undisturbed, while the lighter mass reverses its velocity. So we have discussed collision one dimension. First we consider inelastic collision, and second one we have considered elastic collision in one dimension. These are the cases. In the next session we will discuss the collision in two dimension. Thank you everybody for watching this video.